modified boots concept. This modified boots concept is something and another name given is recoding, or what you say, recoded multiplier. We can say it's a recoded multiplier also. Okay. Actually, here in your boots multiplier, we were taking the bits of qi minus 1 and qi sort of thing, and we were assessing whether what is the action to be taken if both bits are 0, 0, 1, 1, 0, 1, 1. Okay, this was the what you say, the conditional assessment what we are taking, based on which the iteration of either adding or retaining the bits we have done. But here in this boots modified element, we will take 3 bits together. Earlier it was 2 bits. Now what we'll be taking is something like qi minus 1 or minus 1 q of something. Sorry, can I take this in another form? I'll put it in another form. Will be done. What is this? I'll let you know. Bit pair recoding. Something like if a transition, something like a bit from previous stage to the present stage, if you are taking a transition from this direction, if you consider 0 to 0, I'm taking this transition 0 to 0 or 1 to 1. That means 2 bits we are trying to take. Okay. If it is 0 to 0 or 1 to 1, the pair value what we give is 0. Meaning that there is no change in the what you say, the magnitude of the value what you are considering. Okay. And if it is 0 to 1, this direction, if you are taking 0 to 1, qi minus 1 is 0 and q naught is 1, then that recoding of that bit pair is minus 1. If it is 1 to 0, that bit pair is plus 1. 1 to 0, it is plus 1. 0 to 1, it is minus 1. 0, 0 or 1, 1, it is 0. Okay, this is first set. What we are taking is for the first pair and the second pair, we try to recode. Okay, and when you get 2 different values for the bit, what you say, the recorded multiplier pair, again this bits, the values will be evaluated. Something like if it is plus 1 minus 1, say in this comparison 2, you are getting plus 1 minus 1. This will be equivalent to 2 plus 1. Means that it is plus 1 means 2 power 0 position and this is 2 power 1 position. Plus 2 minus 1, it is plus 1. Something like minus 2 plus 1 if it is there, or some, sorry, not minus 2 plus 1. When you are taking the recoding multiplier, it is minus 1 plus 1, say. If you are getting this, means that this is 2 power 1. So 2, that means minus 2 it will be. And this is 2 power 0, that means 1. So minus 2 plus 1 is minus 1. So the bit pairing of recoding will be done based on this evaluation. Recoding will be done with the 3 consecutive bits, taking 2 bits at a time, with the bit values being both 0 or both 1 taken as 0. 0 to 1 will be -1, 1 to 0 will be +1. Okay, so after doing so, we try to take the bit pair recorded format of the total magnitude of the multiplicate or multiply. Anything like ulta you do, n into m or m into n means the same for multiplication. So the one what you are taking as a multiplier, that magnitude we are trying to do a bit pairing so that the number of iterations comes down. The number of iterations will be coming down. Something like this. Say an example, let me take something like say plus 14 is there. Say I'm taking 14. 1, 2, 4, 8. Okay. What is 14? A little bit bigger value. Let me take 14 is too small. Say 45. 45 is there. 45, 1, 2, 4, 8, 16, 32. So what is 45 now? 1, 0, 1, 1, 0, 1. Okay. Now, actually, if you take this as a multiplier and multiply that with another 6-bit value, what happens is what will be the number of iterations or how many times you need to get the partial product, how many times of additions you need to do. A quick answer, please. 6-bit into 6-bit if you are doing. How many partial products? 6 partial products, na? 6 bits I am taking. Bits. 6 bits into 6 bits. 6 partial products because each bit is one partial product. Such type of partial products you will be having 6. So again, what you have to do, you need to do addition. Full additions you will be doing. So how many bit addition you need to apply depends on how many number of partial products you have. So the number of what you say deriving the partial products and doing the addition also will be more if you take all the bits together. Instead, if you do a bit pair recording, the number of bits or the partial products will come down because see at a time what we try to take is we try to take 3 bits together and only one bit pair will be generated. 3 bits in place of 3 bits, 1 bit pair means you are cutting down 2 iterations, 2 partial products you are cutting down there. Only one partial product derives all the 3-bit equivalent value. 3-bit equivalent iteration that is supposed to be done without bit pair. Okay, so something like how we try to take is when we are doing a recording of this thing, we need to take the ith position will be given the bit pair value. Ith position will be getting the bit pair value. So something like this. So if you are taking this elements, these 3, what is the value you'll be getting? Let me know. 1, 0. Or let me give a table form so that it will be a quick reference for you. Okay. So multiplier bits for pairing. Recoded multiplier and bit pair. Bit pair you can say at ith position. Ith position. Okay, where do you take that bit value? Okay. So okay. That means I minus 1, I and I plus 1 I am taking. If 0, 0, 0, 0, 0, 1, 0 1 0 0 1 1 1 0 0 1 1 1 0 1 1 1. These are all the possible bit values we are taking. So 0 to 0, something like bit pair is that I plus 1 and I take. Okay. So here this is 0 0 0 0 0. This is 0 0 0. I'm taking, you can refer to this thing. 1 to 0. 1 to 0 means plus 1. 0 0 0. Again, we need to do the bit pair. Okay. This is recoding we are doing. And 0 to 1 minus 1. 1 to 0 plus 1. 1 to 1 0. 1 to 0 plus 1. 0 to 0 0. 0 to 1. 0 to 1 is minus 1. Next 1 to 0 is plus 1. 0 to 1 is minus 1. 0 to 1 is minus 1. 0. And this is 1 1 1 1 0 0. Now, as I said, the evaluation how we take is this is regarding to 2 power 1 and this is 2 power 0 sort of. So 0 0, what will be the bit pair if you take 0 plus 0 sort of thing? So 0. This is only 2 power 0 position, so plus 1. And this is 2 minus 1. So this will be plus 1. And this is plus 1 in 2 power 1 position. So this will be plus 2. Plus 2. I'll tell what is that plus 2 or plus 1 operation. And now this is minus 1 of 2 power 1. So minus 2. And this is minus 2 plus 1. So minus 1. This is minus 1 into power 0. So minus 1. And 0 0 0. Okay. Whenever it is 0, it is direct the value of what you say, the multiplier directly you can take m. Okay. If it is minus 1, it is minus 1, say this one. For this, it is the 2's complement of m. That is your multiplier. Or your multiplicand, whatever the value, the magnitude. Plus 1. Plus 1 is, sorry, this should be 0. 0 means 0 only. 0 will be 0. Because 0 into anything is 0. No? Here it is m. The magnitude of m. 1 second. Yeah, where did we stop? Yeah, plus 2 means plus 2 is something like we add 0 to the magnitude. Add 0 to the magnitude. That means shifting one bit towards left. Okay, so add 0 to m. This is adding 0 to complement, 2's complement of it. Okay. Plus 1, their direct magnitude, 0 means 0, minus 1 means 2's complement of the magnitude, plus 2 is appending. That means you are shifting one bit towards left. Means that you are increasing that by one magnitude, 1 bit magnitude. 2 plus 2. Minus 2 means for the complement value. Okay. So how to proceed with the evaluation is, now as usual we are taking the accumulator and the Q, and this Q, okay, the size of this will be something like how you will be evaluating this. Maybe flowchart is a little bit that gives you.
Ma'am, can you please explain the rightmost column once again?
Wait, 1 second, 1 second. Which one? This one? Uh, this one,
Yes, ma'am.
bit pair column.
Yes, ma'am.
Yeah. Uh, how to obtain is understood? How to obtain is understood, or that is the doubt?
No, ma'am. The bit pair one, ma'am.
How you consider these values, no?
Yes, ma'am.
So this multiplier bits, this is regarding to what, how to consider the multiplier value when you are doing the iteration of, say, A into B sort of thing. Either if B is your multiplier, okay, or to be specific, M itself you take. M is a multiplier, say. This M value, are you considering that as a direct value, or its 2's complement value, or 2's complement plus 0 value? Direct value is plus 1 means, if this bit pair value is plus 1 means, directly we try to take the multiplicand value directly. If it is minus 1 means the 2's complement value will be considered. That means partial product we are defining. No? So that partial product value we are specifying here. Whether the partial product is the direct value, or its 2's complement, or a 0 added to the 2's complement. 1 means a direct value, plus 1 means. Minus 1 means it's the negation means 2's complement. Okay. 2, if you are getting a value is 2 means it should be appended by a 0. 0 means to say a value, if it is something, a 4-bit value of 0 or a magnitude, you need to append a 0, means that you shift this and you will be adding 0. For this, the magnitude will be added. Like this magnitude is the 2's complement. 2's complement. If it is minus 2, append 0 for the 2's complement value. Okay. If it is plus 2, just add 0 to the direct magnitude. Negation, blindly you can remember this way. Negation, if it is there, it is 2's complement form. Okay. Negation with 1 means 2's complement value. Negation with 2 means 2's complement with added 0. The other things is direct only. Plus indicates a direct value. 1 is a direct magnitude. 2 means it is appended with 0. Whenever there is 2 means it is appended with 0. I'll give you an example there. With that you can understand also properly. Okay.
Okay, ma'am.
I'll give you a flow chart sort of thing. So taking n number, n is the number of bits in the magnitude or the value. Like we try to take something like A, B, Q minus 1. Okay. And this is something like what you can say is A is the accumulator, okay, multiplier and multiplicand. That bit pair, for evaluating bit pair we are taking this. These are set of n bits, okay. Now what we have to do, consider 3 bits together.
Ma'am,
Yeah, yeah, you can ask your
ma'am,
uh,
ma'am, is -2 is also appending or just adding?
mi- minus 2 is 2's complement added with 0. Minus indicates complement.
So only +2 is appending 0.
Plus 2 means no, plus 2 means direct appending, direct adding 0. Minus 2 means adding 0 to the 2's complement.
Okay, ma'am.
Plus means direct value, okay. Minus means 2's complement. Okay, this much is clear. 1 means direct value, 2 means add 0. Now plus 1 means direct, plus 2 means the direct value added with 0. Okay, next minus 1 means the 2's complement. Minus 1 means the 2's complement, and minus 2 means 2's complement add with 0. So I'm writing the values 0, 0, 1 or 0, 1, 0. How many we can get is 1 set, 2, 2, 4. 4 decisions. That needs to be done. Okay. 101, 110. I'm taking with respect to this table, I'm writing this flow chart. Okay. 011, 100, 000, 111. Okay. Like if it is not visible, I'll make it small. I'm writing this chart, this flow chart with respect to this table. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. 7, 8 finished. So now, what are the iterations that has to be performed? If it is 0, 0, 0 or 0, 1, 0, check it here 0, 0, 0 or this 0, 1, 0. This is plus 1. No? Plus 1 means you need to take A plus B. Okay. And if it is 101 or 110, 101 or 110, this is minus 1. Minus 1 means take A minus B, means this is complement. This is complement you are adding. Next one, next block. 0, 1, 1. 0, 1, 1 is plus 2. Plus 2. Actually, this is A is added with A plus 2B. 2B means appending with 0. Okay. One zero zero is minus 2. Minus 2 means A will be stored with A minus of 2B. That means we add the B value with 0. Okay. And that too, that will be the 2's complement. If you take that, becomes the subtraction. Okay. If it is 0, 0, 0 or 1, 1, 1. Okay. It is an operation of A plus 0. That means nothing. As it is, A will be the same as it is. Now, after doing these iterations, the next step is that left shift A. Okay, making your I minus bit 0. Okay, left shift making I minus 1 bit will be 0, making that to be 0. Okay. And finally, what we need to do is that I greater than the n number of bits. That means only for n bits we are trying to take bit pairing sort of thing. So if it is true, then you stop. If it is false, or where should you go? Again, you take that 3 bits. Proceed to the next 3 bits. Okay, so first 3 bits you take, decide the ith bit position. Next, move to the next ith bit position or 3 bit positions, and again try to find the value. Maybe an example, if we can take, it will be little bit more explanative. Okay, 45 somewhere I have taken. Okay, let me take 45 into 12. Okay, let me take this as positive and I'll take this as negative. Let me see how you will be proceeding. Minus 12. Okay. Minus 12. So what is plus 12? Quickly give the value. With the sign bit we are taking, along with sign bit we'll take. Actually, what is 45 plus 45? Let me take how many bits it will be in need of. Sign bit also will be taken. Sign bit is one bit added. So at least we need 7 bits now. Is it 7 bits? 45. Sign bit is 0 plus I am taking. So 1 0 1 1 0 1. Is this correct? I hope this is plus 45. Next plus 12. 0 0 0 1 1 0 0. Now minus 12 if you take minus 12. Minus 12 is 0 0 1 0 1 1 1. Along with sign bit I am taking. Okay. So now what I am doing is, for this minus 12, I do that bit pairing. I do the bit pairing for minus 12. Okay. And see here. This is minus 12. What is this bit pair? 0 0 and 0 1. 0 0. That means 1 0 0.
Minus 1 0.
Bit pair. So what will be the bit pair in total? Okay. So how we proceed is, what is this qi minus 1 is there now? When we were taking, this is total q 1 1 1 0 1 0 0. What I said, minus 1 is there now. So if this is 1, minus 1 will be here. So this is 0 1 2 3 4 5 and 6 if we are taking. This is minus 1. So we try to take first this as 0 initially. So make this 0. Now, when we are taking this bit pair or pairing the 3 bits, in the ith position, the bit pair will be occupied with this value. See here, ith position we are saying here, this ith position. So this ith position means where it will be. This will be the ith position. This will be the ith position, now. -1 I plus 1. So at this position we'll get a value. Okay. So first we are considering these 3 bits with a 0. Added with 0 will be for every value, initial iteration. So 0, 0, this is 0, 0, 0, this is 0. In total, it will be 0. So in this position, it will be 0. Okay. Next is we take this position, or what you say, this 3 bits. When you are taking these 3 bits, this is the position where you will get the bit pairing. Now 0 to 1 is -1, 1 to 0 is +1. Am I correct? 0 to 1 is -1, 1 to 0 is +1. In total, it will be +1. Okay. Next, we'll take this pair, and this will be the position. Now, this is 0 to 1. 0 to 1 means -1. 1 to 1, it is 0. 0 to 1 -1. 1 to 1, this is 0. Now, what is in total? It will be -1. And finally, you'll be left with this position. Okay. Now, what is the final value? One, 1, 1. What is that? 0, no? 1 to 1. This one. 1 to 1. 1 to 1. 0, 0. So, in this position, it will be 0. You got this now? We are taking the 3 bits together. Now, this is the bit pair recorded value of -12. This is the bit pair recorded value of -12. This is -12. Actual, this is -12. This is extra bit what you have taken. For this, we are getting a bit position. This is the least bit position, and this is the maximum, like LSB to MSB sort of thing. Yeah, any doubt?
Ma'am, once repeat how you got a Q6 such a number. Like how you generated qubit, ma'am. Once repeat that.
Which one? This total one, huh?
Yes, ma'am. Once.
This is 3 bits together we are considering. Okay,
No,
3
ma'am.
bits
I'm asking how that number. How you wrote that number once?
this one. This one or this one? First, this is 12, -12.
Okay, ma'am. Now I get it.
This is -12. This representation. Because this is -12 we are taking, no? Okay. Now, 45 into -12 means, what is 45 plus 45 we need to take? Plus 45, this is 0, sorry, 0, 1, 0, 1, 1, 0, 1. Okay. Now, that is the reason, like, what is the maximum magnitude, how many bits you have, that should be the size of both the bits or both the magnitude. Okay, though 12 needs less bit number of bits, we are taking full 7 bits. Okay, that is the reason. Now, after bit pairing, these are the values what we are getting. So now what we do is in the bit positions of this, we try to take this bit paired value. Okay, bit paired value, and this will be +1 here. The same positions I am taking, and this will be this position. It will be -1, and this position it will be 0. The same positions we are taking. And now you see 0 means it is 0 directly, and how many bits we need to take is 2 times of n, because this is multiplication. No, we get the resultant as 2n. So 7 means 14 zeros I am taking. 6, 9, 12, 13, 14 zeros. Okay. Next, where you have to start is the next partial product should start from not the 1 bit shift, but it is the second bit shift. Here we have taken, no, you shift left shift towards the next bit value. So from here we'll start. +1 means it is direct value. So directly you'll take the value of m. Now what should be these values of sign bits is the sign extension will be done. What the sign bit value is, the same will be extended towards the remaining bits. This is sign extension. Okay, next iteration is -1. -1, what we said, it is the 2's complement of the multiplicator. 2's complement we have to take. So where to start is 2-bit shift now. This is 2-bit shift. From here we need to start. And this says it is the 2's complement. So 2's complement is this one. For this is 1 1 0 0 1 0 1. And you extend the sign bits. Oh, sorry. Extend the sign bit means it should be 1 now. Because here this sign bit is 1, we need to extend that sign bit. Got this? What is sign bit extension? The same sign bit value will be extended towards the what you say leftmost side. That is your appending bits towards the most significant bit positions. Now this is anyhow 0. Actually, if there is some other value means we need to take from here only. But this is 0 means we need to take multiplied with that value. What is the partial product you get is 0. Okay. Now, what is the result we will be getting when it is 45 into -12 means what is the result? Minus negative 45 12s. It is I think 540. Minus 540. What is minus 540? What is plus 540? First of all, you have to take what is plus 540, and from that what is minus 540. Minus 540 means 2's complement of plus 540. Now, am I right? I think if you take 1, 2, 4, 8, 16, 32, 64, 128, 256, 512 sort of thing. Appended with sign bit I am taking. 0 is sign bit is positive. 0, 0, 0. I think 32 also 0. 1, 1, 1. If you take that becomes 20 plus 20, 40. 540. Now minus 540 is 2's complement of that. 2's complement means this is 1, 0, 0, 1, 1, 1, 1, 0, 1. This should be the answer what we need to get here. Okay, because the result is in negative form, because plus 45 into minus 12 we are doing 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. Is this correct? Correct, na? This is minus 540, na? This is, see, until this we have same result. This is sign extended value. If you do the 2's complement of this, you will be getting plus 540. This is minus 540. You check it out if you want. Sign extended value, this one.
Ma'am, I have a question.
Yeah.
How do we know where the sign extended bit starts?
How do we know that?
Like in this example, the last three ones are the sign bits,
Ah,
right?
in the sense,
Yeah, how
in
do
that
we
way,
know?
yeah, got your question. See, this is the negative value. All ones towards your MSB indicates that it is negative value. Okay. If you do the complement of this, you will be getting the positive 540. Your all values of towards your MSB, actual partial product, if you take if you multiply n into n, the magnitude in the binary format won't be complete what you say 2n magnitude size. It will be less than that. Okay. Your most significant bits, if they are 1, indicates that your answer is negative or your result is negative. Okay. In order to get the positive number or its equivalent in positive, you have to do the 2's complement. You'll get back this original value. That means if I do that 2's complement, what I'll be getting? So this is my positive number now. What is this value? This is this one is 4, 8, 16. That is 100. And this is 512. Now that this is plus 540 now. Towards your leftmost side, that means MSB side, if it is 0, that bits are zeros, indicates that the result is positive. If the bits are 1, it indicates that it is negative, because anyhow we are doing sign extension. That itself indicates that the result is negative. If you want to find the magnitude of the result, you have to redo the what you say, the 2's complement of the negated value. You will be getting the positive magnitude. Hope I'm making some sense in answering that.
Yes, ma'am, it's clear.
Yeah. So you're when you're checking a negative number, in the result will be given with a 1 value. So you do that with positive numbers and check it out. Yeah. Say plus 45 with plus 12 if you are doing. Your result also will be plus 540. That means this will be the result. That means here your leftmost bits will be 0 direct. That is the assessment even will be doing by checking the result in a blindfolded format, whether the result is positive or negative. But magnitude evaluation, you need to evaluate based on the bit position once. Okay. So this is something about your modified Booth's algorithm or recoded multiplier. Okay, you do take the help of this table and flowchart. Again, with your own example, you try to evaluate and see whether it is working or not. Okay. The next one is restoring division. The other one is non-restoring division. Actually, why we are taking so many so much pain in learning all these things is we need to find a method wherein the iterations complexity is coming down. That is the only aim for doing other methods of division, multiplication, or addition. Okay, why we are not taking only the direct adding format, or what you say, repeat adding to get a multiplication, or repeat subtraction to get a division sort of thing, is the number of iterations, the steps involved. Want to cut down that, and with simple few steps we want to find the multiplicand element or a divided element. Okay, so another form of division, like division normally we take is repeated subtraction. Yeah, only with adder, if someone wants you to implement a divider, how you perform, you do a negated addition repeatedly. Negated addition means complement addition, is subtraction. Repeat the subtraction multiple number of times becomes the division. But that process is very huge. Like you need many more iterations, many more steps involved. All that becomes very clumsy in hardware point of view. So we need to go for some simple formats of getting that division or multiplication. So this restoring division or non-restoring division is something like by the format of checking whether the what you say, the partial element that you are getting is less than a zero value or more than zero value. Less than zero means negative number, more than zero means positive number. Okay, say if you are I'm taking that in this format now, dividend and divisor format. If you take, say dividend is, say I say it as Q and the divisor is B. Okay, and A is anyhow accumulator for storing the data, or what you say, the partial element what we have. Now, how we try to proceed here is, here we are not taking any extra bit, only A and Q will be taken. A and Q will be taken. We try to manipulate the value of A based on whether the value, that means the stored value is greater than zero or less than zero with the divisor. Okay, let me give you a flow chart sort of thing, or else what to do. Let me explain. Say you have some 4-bit magnitude divider and divisor. Take one extra bit in the accumulator to indicate or sign. Okay, and this sign bit will be deciding whether to add this B value to A or subtract this B value to A. Okay, add the B value to A or subtract the B value to A. And not only that, we do a left shift here. Previous examples, Booth's multiplier sort of thing, we have taken right shift, but here we will be doing the left shift. Okay, left shift with restoring or with non-restoring aspect we are doing. When we are doing the left shift means these bits will be moving towards this direction. There will be vacancy of bit in this Q naught position. If this is Q naught, Q1, Q2, so sort of thing. Now, what should be the value of this Q naught will be decided by what is the sign of the A, or what is the sign bit of A. If this sign bit is 1, indicates that if sign bit is 1, if this value Q naught as 0. If sign bit is 0, it indicates that that magnitude or that value is positive. Then we need to make this value as 1. Okay. So I'll give a flow chart. The flow chart, something like start. Okay. Take, as I said, A is accumulator. Take Q as the dividend and B as the divisor. Okay. Then how many number of bits you have? That is N is the bit count. That means how many iterations we need to perform is decided by this count. Okay. Now what we do is first we take the values of, okay, A is given all zeros. First we'll give all zeros. In Q we try to take the dividend. Okay. Then what we have to do is the next step is that shift your total A and Q towards left. That means both the bits, that means say 9 bits together, you shift them towards left. Doing so, you'll be discarding the sign bit. Okay, and here the vacancy will be arising. Here the sign bit will be discarded. If you are doing the left shift, the vacancy comes here. When you are shifting, you will be checking what is the value of sign bit. Okay. Next, what you have to do is after shifting, try to do the ones complement addition of the divisor. Sorry, two's complement, not ones complement. We are not taking ones complement. Two's complement of the divisor and check whether this last bit I'm saying, this A bit, say A5, AS I take, AS is less than 0. If it is less than 0, true. It is not less than 0. If less than 0 means it is negative, na? Negative. You have to make the value of this Q0 bit, to be 0. That means if it is true means sign bit, this will be 1. And you need to restore back. Now we are taking this restoring division. Restore back the value of A means first we have subtracted, you need to restore back means again you add that B. You will be restoring back the value of A. Okay. Now if A is greater than 0, that means false means A is greater than 0, it is a positive number. Then just you make this Q0 value to be 1. That's all. No other iteration is needed. Next, after performing this, you need to decrement the counter. You need to decrement the counter. -1 you do. Okay. Then you check whether the count is complete or not. Complete in the sense, say how many number of bits you are taking, and if that many count is complete. If count is 0, if it is true, stop. If it is false, then go back. Where to go back? We need to go back to this point. So these are the needed iterations. So I'll take one example now. Say Q is 1010. What is this value? 1010.
10.
10. Next, I take, say B is 1100. Means 3. So what should be my quotient and what should be my remainder? What should be my quotient and what should be my remainder? Remainder should be 1. Quotient should be 3 now. 3 is 9. Remainder will be 1. So this should be my result when I do the division of 10 by 3. Okay. So that we need to get using this restoring operation. Okay, restoring division operation. Okay, so let me take A and Q. Say Q is 1010, and this we are taking 4 zeros plus 1 sign bit. Now, what is the next operation we need to do is left shift. We are saying left shift all the bits. So doing so, we discard this first bit 0, 0, 0, 0, and this one comes here 0, 1, 0. Now this bit is vacant now, and this vacancy will be filled by what is the value you get after doing the operation of this one. This one you need to do the 2's complement addition of B. What is the 2's complement of this fellow? Along with sign bit we are taking. You know, this is sign bit we are taking. Say this is sign bit also added. 2's complement of this is 10111. You add this one. You add this 11101 and see what is the result you are getting. Okay. Now what we have to see is, I said you have to see this is AS bit, AS bit. So this AS bit is 1 indicates that this is less than 0. AS is less than 0 makes your Q naught bit, this is Q naught bit, to be 0 or 1. This makes this bit to be 0. So finally what you get is this value. Okay, and here you need to restore, means that you need to add this back B value. When you are adding the value of B back here 0, 0, 0, 1, 1, what is that you get? 1, 0, 0, 0, 0, 1 you discard. Okay, now this is the result of the first step. So now we have finished the first step. Decrement the count. Next, again, because we didn't complete the complete iteration. Next, move AB, AQ, one left shift, one more left shift. So 0, 0, 0, 1, 0, 1, 0, 0. Now this Q naught is vacant. Now add this 2's complement of B 1, 1, 1, 1, 1. Again, this AS is less than 0. So this Q naught will be 0. So you have to restore this back. Restoring means add B back. You'll be getting this as 0, 1, 0, 0, 0. And you'll be discarding that one, whatever you are getting there. So what is the value you get? This is your second step. Hope you are able to follow the iterations what we are doing here. So second step is complete. One more, next step. Shift this towards left. Shifting so you'll be having 0, 0, 1, 0, 1, 0, 0, 0. This is vacant. Now add that P's complement 1, 1, 1, 0, 1. You'll get this as 1, 0, 1, 0, 1, 0, 0, 1. Discard this. Now see here, AS is greater than 0. Why? Because this is 0 indicates positive. So if this is positive, your Q naught will be 1. This Q naught will be 1. Because of that, Q naught will be 1. Q naught will be 1 means that we don't need to add B bit again. Okay. So finally, what will be the answer in this step is you'll be getting this as 0, 1. This one is 1. Okay. 0, 0, 0, 1, 0. This is our result of addition, and this is the value what we attained with Q non bit. Okay, now do the left shift. Is this correct now? Do the left shift. This completes the third step. Left shift means 0, 0, 1, 0, 0, 0, 0, 1, bracket. Now add the complement value of P, discard the carry. Now this is A is greater than, AS is greater than 0. So this becomes 1. There is no need for us to shift, or what you say, the restoration is not needed. This is the result here. Okay. And see, I think 4 iterations are over now. 1, 2, 1, 2, 3. This is the 4th iteration. So 4th iteration, your count will be 0. Now, the value that is stored in A, this is the value stored in A, this is the value stored in Q. The value that is stored in A is the remainder, and the value that is stored in Q will be the quotient. So decode this back. This is 3, this is 1. So 10 by 3 is 1. Correct? 3 threes, remainder is 1. 3 threes are 9, quotient, remainder is 1. Correct? Any doubt?
Ma'am,
Yeah.
how did we decide to do 4 rounds again? Is it because there are 4 bits in Q?
Which one? Which one? Can you repeat your question
We
in
did
a louder
4
voice?
we did 4 iterations, right?
Yes. Yes.
Did we decide that based on the number of bits in Q?
Yeah. This is actual. What is the size of the magnitude we are taking? 4-bit we have to taken now.
Yes, ma'am.
And for A, we are having one extra sign bit. There is only one added element, but number of iterations is equivalent to the number of bits of your Q. Q or A, but A is added with sign bit. The sign bit you have to remove. Only the magnitude bits only we are considering. Number of magnitude bits.
Okay, ma'am. Thank you.
Okay, I'll stop here because the other non-restoring, again we need half the. We'll continue and take the assignment questions. You need to take an example from of your own choice. You define the Booth's algorithm, the approach of Booth's algorithm with your own example. Modified Booth's algorithm with an example evaluated. Restoring and non-restoring division. These are 2 questions, 2 different questions. You need to answer that with the corresponding flowchart and example. Okay, different example and the corresponding flowchart you have to give. Restoring and non-restoring. Non-restoring, anyhow, next week I'll complete, but take the question. Okay, no further queries, we can stop.